Okay, well, I believe we have an hour, so I'm going to spend the next 45 minutes just introducing myself and Emily. Emily and I are together at UCT. We're doing the Applied Marine Science Masters course together. And this was actually part of our course, a small part of our course. And we were luckily given it to speak on, and it is, in fact, one of my favorite sections of Habitable Planet. And to sort of follow on from what Nazira and Daniel were speaking about, and to explain why our atmosphere is so important, I'm going to continue to look at this graph and at our neighbours in the solar system. Now, in a very relative sense of the word, Venus, Earth and Mars are approximately the same distance from the Sun. And this means that they formed out of the same material and had approximately the same initial temperatures about 4.6 billion years ago. Long ago, these planets probably had moderately enjoyable temperatures for life, but as Goldilocks would put it, Venus is now far too hot, Mars is too cold, and only Earth is just right. Venus is approximately the same size as Earth and has about 82% of our mass. It also has a rocky crust and an iron nickel core, but that's where the similarities end. Venus has a very thick atmosphere made up of about 95% carbon dioxide. The rest of it is nitrogen. And if we had to put it simplistically, I'd like you to think of Venus as having a very thick, fluffy duvet as its atmosphere. On the other hand, we have Mars, which has an atmosphere about as thin and as effective as a sheet. Mars' thin atmosphere, which is about just under 1/100th of Earth's atmosphere, does not trap much heat at all, even though it has the same composition as Venus. Because it is so thin, the greenhouse effect is negligible. In fact, and I have this very interesting fact, Mars has such rapid cooling between day and night that the temperature can change by as much as 80 degrees Celsius. I think that's quite remarkable. Now, if we look at Earth's atmosphere, which this is an image you've already seen from Nazira's presentation, we have an atmosphere that is made up of 78.8% nitrogen, 20.95% oxygen, and 0.93% argon. These three gases make up approximately 99.96% of our atmosphere. Carbon dioxide, methane, ozone, the hydrocarbons, and other gases in the air are what we call trace gases. And carbon dioxide is the most abundant of these at about 0.03%. To give you an idea, for every million air molecules, you will usually find less than one of carbon dioxide. So it's there in very minute amounts. But that doesn't mean it's unimportant. I'd go as far as to say that it is vital. Now, I know you don't know me very well, and you don't trust me, but I need you all to close your eyes. Just close your eyes. And now I want you to imagine that you went outside this morning and you looked up at the sky. What did you see? You saw a yellow sun in a blue sky. Now imagine that you're on the moon, and you're looking at the same thing. But what do you see? Well, in fact, you see a white disk, an endless black. But how can that be? You're looking at the same sun through the same atmosphere. Before I can even begin to answer these questions, and you can open your eyes. Before I can answer these questions, we have to grapple with a few fundamental questions, namely, what is light? What in fact is colour? And what does our atmosphere have to do with any of this? And for that, I'd like to introduce Emily.
We started with the question, what is light? Something we almost take for granted. We couldn't see each other's day if there wasn't any lights. But this is something that has taken 3 centuries and 3 extraordinary scientists to fully unravel the phenomena of what we, the scientists and physicists, call light today. In 1666, Newton brought a prism to try and understand the concept of colours. So he shone a stream of white light through the prism, which refracted and essentially the rainbow colours along the other side of his wall. From these and other optical experiments, where he nearly blinded himself in the process at times, Newton proposed that light is a stream of particles, and that the colour we see is the light that is the colour of sunlight that the body reflects. So sunlight is made up of all the colours. However, the light is a stream of particles was the first theory of light. It couldn't explain all the phenomena of light, but it did give a good reason for a couple of the key ones, refraction and reflection being 2. The idea of interference patterns of light was something that Newton couldn't answer. So in 1678 and in the 1800s, both Hudgens and Young and Fresnel proposed that light is a continuous train of waves. Hudgens proposed that shining a stream of light through a tiny slit in the screen was able to show that light streams out. So like a triangle, just like you would shine a torch, and that light goes out. It doesn't go in a straight line like a particle. If light was a particle, it would. Young and Fresnel took this a bit further and did some split screen experiments where they explained the interference pattern through that. The best way to describe the interference pattern, and if they surface in the moon's day, so if you're riding an ocean wave, you're going along, the second one comes from a different angle, you end up with them colliding and creating sort of interference pattern. The surf has to be careful not to wipe out, but this is the best way that they were able to explain. So they were able to explain the interference pattern seen when two beams of light are shone through and they collide. Young and Fresnel proposed the concept of a wavelength, and that colour corresponds to different length wavelengths or size wavelengths.
The light that we see with our eyes is in fact a very small proportion of an entire electromagnetic spectrum. 1,000th of a percent, in fact. The human eye is not capable of actually seeing radiation with wavelengths outside of the visible spectrum, and only electromagnetic radiation with a wavelength between 380 and 760 nanometers is detected and perceived as visible. Just as we accept that colour is associated with emotions, red for passion and green with envy, so too must we accept that that different colours correspond to different wavelengths. Sunlight is a superposition of all the waves of light. In other words, all the colours of the rainbow that are travelling through space in a straight line. All these visible wavelengths move through the Earth's atmosphere, however, and only stay in direct trajectories until they bump into airborne dust or gas molecules. What happens to the light now depends firstly on its wavelength, and secondly on the size of the particle that it strikes. At the one end of the spectrum, and now I need Emily, we have short blue wavelengths, and on the other end of the spectrum we have long red wavelengths. Don't make me jump up and down just now. And the first time we did this lecture was an entire coincidence, and we happened to be wearing these things, but it worked out very well. So now when all of this light passes through our atmosphere, photons and molecules in our atmosphere interact with it through scattering. Oops. Visible light. Scattering. There we go. The rule of scattering is simple if the particle is small relative to the wavelength of the light. The smaller the particle, the less chance it has to interact with long wavelengths, but it will definitely interact with the smaller ones. The tiny gas molecules that make up our atmosphere are relatively small in comparison to the red, but are relatively big in comparison to the tiny little hobbit blue waves. Okay. When light bumps into gas molecules travelling through the atmosphere, the smallest, shortest wavelengths are scattered. Hence, blue skies for those living on Earth and a beautiful blue planet for those observing us from space. So to bring us back to the question I asked at the beginning, why is it a black sky and a white disk instead of a yellow sun and a blue sky? Well, the moon has no atmosphere with which to scatter light. Of course, it is somewhat more involved than that. As sunlight streams through our atmosphere to reach Earth, Earth also radiates infrared back into space, which is invisible. Instead of being lost to space, much of it is absorbed by the atmosphere, which now acts as that blanket analogy that I mentioned earlier, to retain just the right amount of heat. And this is called the greenhouse effect. And it's made possible by the fact that wavelengths of incoming visible light have different wavelengths to the outgoing infrared. And the different wavelengths are a consequence not only of colour, but of temperature. As temperature increases, the dominant colour systematically moves through the spectrum of the rainbow, from red to yellow to blue. The hotter a body, the shorter the wavelength of its principal colour. Our sun emits, as we know, yellow predominantly, and the cooler Earth emits long infrared. For our atmosphere to provide us with this very, very important greenhouse effect, it needs to be able to distinguish between the short waves of visible light and the long infrared waves given off by Earth's surface. Well, how does it do that? It's not about speed. No matter how different the wavelengths are, light still travels at the speed of light. So how does it do it? If you look at this image, you can see black metal that's been heated to very high temperatures and is now giving off a red glow. If you think back to what I mentioned just now about wavelength and temperature, well, this is thermal and its equivalent electromagnetic radiation at work. So if Emily and I now changed our shirts, and I wore white and she wore black, and we then went and sat outside in the sun for an hour, her shirt, as Daniel mentioned in his answer to the question earlier, would absorb all of the sunlight and all of the heat, and after an hour she'd be uncomfortably warm. I, on the other hand, wearing the white shirt, would remain relatively cool because I would be reflecting the light and the heat. The reason for this is that black objects are the best at absorbing all of the light falling on it, and they emit practically no visible light in return. Now, in physics, the ideal thermal emitter is called a black body, and because scientists aren't poets, the radiation that they give off is called black body radiation. And if you can keep the image of a Bunsen burner in your mind, and this image up, which is quite cool, as the temperature of a body increases, the color it radiates will change, going from red to orange to white and then to blue. But it never gets invisible. It gets really, really hot, and the wavelengths get really, really energetic, but it never gets invisible. And before the 1900s, classical physics couldn't come up with a reason why this was taking place. Max Planck came to the rescue, putting forward the first model to explain the full spectrum of thermal radiation, and proposing that energy is quantized. Planck proposed that the different colors respond to different quanta, or energy packets, or units of energy, sorry. Long red wavelengths have small quantum energy, so I'm super chill and lazy. But blue wavelengths are really energetic and highly energized, and that is actually true of our interaction in our master's course, by the way. In 1905, Einstein took Planck's work further by suggesting that energy in a beam of light occurs in individual packets called photons. Einstein's photon theory was obviously met with a bit of skepticism. I mean, everything up till now has proven and proposed that light is a wave. But it did explain something that had been puzzling scientists for a time, and that was the property of the photoelectric effect.
The photoelectric effect describes how light interacts with matter. If we shine a beam of light onto a metal plate, similar to this one here, we would see that we could create an electric current between the plate and the one next to it. The reason for that is that the light will vibrate the molecules in that metal plate fast enough that the electrons are released and they jump onto the next one without even needing a wire to cross. Experiments have shown that the light that's shone onto these metal plates is not the intensity, it's not how bright it is that causes the electrons to break free, but the frequency of the light, which is related to the color. So along the electromagnetic spectrum again. So so an example of this is that a copper plate will not create the electric current with photoelectric effect from a beam of yellow light, but it will from a weak beam of UV light. To explain this better, we can use the example of assigning money or denominations to different length wavelengths. 1 rand coins for the long infrared wavelengths like Lauren, 5 rand coins for the slightly more energetic yellow light, the photon, and 10 rand notes for the highly energetic UV rays, which will be there. So copper will only accept the 10 rand notes of UV rays. It will not accept any 1 rand coins of infrared light or 5 rand coins of yellow light, even though 10 1 rand coins of infrared will make up a 10 rand notes. So copper and other metals all take up light at a different frequency, or absorb light at a different frequency and interact with it. This energy, in this way that they absorb in discrete units, or discrete denominations, is what Einstein proposed as photons. Energy of light, or photons, is available in discrete units, and matter and gas molecules absorb only certain photons of light, which are related to the frequency of color. That's the same thing there. So the energy, So saying, the shorter the wavelength, the more energetic the photons are. And so how a photon interacts with or is absorbed by gas molecules depends on how energetic it is. UV rays are particularly dangerous for us and can cause sunburn. That's because they're highly energetic and can break the chemical bonds. Like chemical bonds releasing electrons and causing damage to our skin. Okay, so we've got radiation from both the sun and the earth at different wavelengths interact with the gas molecules in our atmosphere. the way they interact depends on the energy of the light waves that are being radiated. We have three examples of energy levels which can interact with like gas molecules. UV rays, which are highly energetic, cause molecules to, and the electric energy levels, cause molecules to chemical bonds to break and photodissociate. This is an example of what happens in the ozone layer, where ozone interacts with UV light and absorbs the UV light before it enters the atmosphere. Vibrational occurs in molecules in the infrared radiation, which is reflected from the Earth's surface back into space, and causes the molecules to swap places and the length of bonds to change in shape. Microwaves have got really low energy and just cause the molecules to rotate. We can think of that as microwaves that we heat our food with. That's what they do to the molecules to warm the food up. The way we can demonstrate how the gas molecules in the atmosphere interact in this energy levels with the different wavelengths of light is the same as I have just demonstrated for the photoelectric effect. The gas molecules will are selective in the type of photons they absorb. They won't rotate at any rate, nor vibrate at any rate, only at the rates, with certain discrete values. So gases can only absorb photons at exactly the quantum of energy that is needed to change it from one state to another. So nitrogen and oxygen, which are, as Lauren has said, the most abundant gases in our atmosphere, are diatomic, two molecules, or two atoms, and can only react with the highly energetic UV rays coming in from the sun's atmosphere. These nitrogen and oxygen react with UV photons in the top levels of our atmosphere, where they photodissociate and ionize. The more complex diatomic molecules, such as ozone and carbon dioxide and water vapor, to name a few, have more moves. They are able to interact with a wider variety of photons or colors of light. And this is how how ozone, which provides a second level of defense, the ozone layer, it reacts with UV light in the stratosphere to dissociating the ozone and absorbing that bright light, protecting us from really harmful UV rays. And ozone also interacts with infrared light radiated from the Earth's surface. And that is what happens in the troposphere. Carbon dioxide, water vapor, ozone, and other greenhouse gases absorb infrared radiation, which vibrates the molecules, absorbing the light that's radiated out, retaining the heat in our atmosphere, and that helps us jump that gap between what we've observed and what we've calculated with Nazira and Daniel. The best way to describe that, and this is a fantastic figure here, this shows the infrared radiation being radiated from the surface of Guam, a Pacific island, into the atmosphere. The jagged line shows what is recorded as radiated infrared light, long wave radiation, out into the atmosphere. The smooth lines show what would be radiated if there were no greenhouse gases and at different surface temperatures, because the different temperature of our surface will depend on what kind of heat is being radiated out. What we can see, and this is the wavelength, infrared radiation is radiated out, and the radiant energy, is that there are these sort of big gaping holes in what is observed from the radiated heat, out into space. This is at 15 microns, it's where carbon dioxide absorbs infrared radiation. And that makes it a very strong greenhouse effect. It's a strong greenhouse gas that is able to absorb low infrared radiation, retaining that heat that's being radiated out. There's another similar sort of hole in the observed spectrum, which is where ozone is found to absorb infrared radiation. And as I mentioned, ozone is a very powerful greenhouse gas that absorbs both infrared radiation and the radiation coming in from the atmosphere, the highly energetic UV rays. Different gases, however, contribute to the greenhouse effect differently. CFCs, which I'm sure all of you have seen, are now banned from our deodorants and refrigerators, is a particularly powerful greenhouse gas because they absorb in wavelengths where they aren't being absorbed anywhere else. So these windows that we have in the observed spectrum allow in sorry. Oh. What's happening?
Just come back.
Sorry.
See, really highly energetic little blue wave.
Alright. Okay, thank you. Oh no, hang on. I haven't come back there. Did it long? No. What is this computer?
Now,
It's a Mac.
what did you do?
Done.
I don't like technology very much. Always does this to me. Sorry, guys. Oh, great. Thank you. Alright, so there we go. We've got the windows, which I'm not going to mess with. The windows here, which allow infrared radiation to pass unimpeded through our atmosphere. If we introduce gas molecules which absorb radiation in these wavelengths and these colours, we're going to cut off these windows and trap more heat in our atmosphere, exacerbating the greenhouse effect. CFCs are a particularly high one because they absorb between sort of 10 and 15 microns. So they contribute but disproportionately to the greenhouse effect. If we add another carbon dioxide or ozone to the atmosphere, they're already there, so they will amplify the greenhouse effect, but they won't be as serious as introducing a new absorber into it. So water vapor is also a particularly important greenhouse gas, as it absorbs infrared radiation over a wide spectrum of wavelengths. However, water vapor is a bit difficult for climate change scientists to sort of model in the greenhouse effect because it varies depending on the temperature of atmosphere. The warmer the atmosphere, the more water vapor there is, the more infrared radiation it absorbs, and the more greenhouse effect it has. However, Earth, and I won't go into that because we're going to talk about later in the week, has special mechanisms to help us to sort of monitor that so we don't go into a complete greenhouse cycle with the water vapor just absorbing more and more infrared. So, that's really the end. So we're saying here, just to conclude, so it's very important, ozone, carbon dioxide and water vapor are three key greenhouse gases. They aren't highly concentrated in our atmosphere, but they do play an important role in maintaining the temperature that we experience today and keeps our planet habitable. Now we're going to go through all that again, sorry.
Okay, I will leave the slide, it's fine.
Alright, yes, so we're going to conclude.
Basically, our atmosphere acts as both a blanket, which I've explained, and as Emily has referred to, a parasol or an umbrella to protect us from harmful rays, such as UV. But it's the interaction between light and air that makes our planet quite remarkable. And it's understanding these interactions that are really important, and this is the take-home message that we'd like to give, is that you cannot begin to understand the process of global warming and the interaction with our atmosphere unless you understand the things that drive it, such as the interactions between light and air. And I hope that we've elucidated some of those processes, and I hope that you have some questions to ask us, because we've got a lot to say, and we had to fit it into a short amount of time, but please feel free to ask us some questions in conclusion.
Any questions about the building picture? This particular.
Yes.
Lauren,
You promised me you wouldn't ask any questions.
no, but this is a question about literature that you read, literature that I read.
Right.
And it's to do with too hot, just right, and too cold.
Goldilocks.
I think it's Red Riding Hood.
No, it's not. Red Riding Hood was the wolf.
Yes. I guess I'll be reading wrong literature.
Yeah, I'm afraid so.
I told you the question would be easy.
Token question.
Okay.
Okay.
Also, I think probably you can do the difference between global dimming and global warming.
Sorry, global dimming. The fact that our sun is not as bright as it used to be. Our sun is in fact getting brighter, isn't it? Yeah. We come from a dimmer planet. The sun is in fact getting brighter.
Is that from Cape Town to Randstad?
The reason that even though our sun is getting a bit warmer, and the fact that our planet isn't warming concurrently, is because of our atmosphere. Because our atmosphere continues to protect us and continues to shield us and act as a buffer to keep it, as habitable as we experience it today.
I have a question.
Oh dear. Okay.
In the previous talk,
Yes.
they calculated the effective temperature of Venus and Mars,
Right.
and the temperatures came out greatly wrong
Yes.
compared to the observations. And I promised you'd explain. We haven't had an explanation.
Well, I mean, I alluded to it somewhat in that Venus has an atmosphere like an eiderdown, like a fluffy duvet, 95% carbon dioxide. So it is exactly as Emily explained. It is a very effective absorber. In fact, maybe you should explain it.
That's all I know.
And so it allows, as it is wont to do, it allows sunlight to come streaming in, but it allows very little, in fact almost none of the infrared from the warm planet to escape into space. So it really gets hotter and hotter and hotter and remains very hot because of this atmosphere. Now Mars, although the composition is very similar, it has as much carbon dioxide in its atmosphere, but because it is so thin in terms of its composition, it is like a sheet, so it keeps losing all of its heat. And I would essentially say Mars has no atmosphere. And so that's why when you look at that, you know what I'm going to try. When you look at that graph of Nazira's and of mine, which we repeated, Mars has a relatively similar temperature to what is predicted using the models. And that's because it has no atmosphere to speak of, and so it is as it should be in terms of conservation of energy and in terms of what is gained and what is immediately lost. I don't know if I explained that correctly. Yeah, well, thick eiderdown. I don't have the graph.
I know.
Okay. Oh, right. Shit, what have I done? Okay, the geologist.
No, the top.
Oh,
Who is it?
okay.
Sorry, I don't know your name.
I'm just asking about the gravity of the planet outside.
Okay.
And can you explain the atmospheres on these three planets?
Okay, well, Earth, as I explained, has water vapor, it has, where are my notes? It has carbon dioxide as a trace gas and a number of other trace gases, and oxygen, and I should know this, don't. Okay, 99.9% of the air is nitrogen, oxygen, and argon. The trace gases, which carbon dioxide is the most abundant thereof, is 0.03%. So carbon dioxide on our planet is 0.03%. It's 96% on Venus and 95% on Mars. So in terms of composition, the greenhouse gas gets a chance to act as an incredibly powerful absorber of infrared on Venus, but doesn't have enough of a chance to absorb on Mars because it's so thin. There's so little of it. It's a sheet, an eiderdown, and we're like a blanket. Perfect blanket. I'm not explaining it.
What I really want to know is, because these planets are different latitudes, for Mars,
Yeah.
gravity from Mars, than that of Earth. Is it not the reason why the atmosphere is so thin?
Oh yes, that's exactly what it is. It cannot be held close to the planet, and that's why even though it has so much carbon dioxide, there's so little of it around because it keeps getting lost to space. That's why it has such a thin atmosphere. If Mars were larger, it would have a much better chance of retaining its atmosphere. And that's why I mentioned that Venus is of a relative size to Earth. It has a similar gravitational pull on its atmosphere. It's just its composition that is the key in that particular example. Okay. Yes.
Sorry to do this to you, but I'm going to make you go back to that graph that was giving you so much trouble.
This
Oh,
one.
okay, hang
The
on.
greenhouse
Oh,
gas.
Guam.
Sorry.
I don't know how you do it. I'll let Emily take on Guam.
Here we go. Okay. Now I'm not going to touch the computer, but what can I...
Just having some trouble trying to absorb it.
Excuse me.
Okay. Wavelength. We're talking about the wavelength of the particles.
Yeah, okay. Of the
light.
infrared spectrum.
Okay.
Yeah.
Radiant energy. Okay. What are those?
So what are the smooth lines?
Yeah.
They show what the radiation would be if there was no greenhouse gases on Earth in the atmosphere and at different temperatures. So this one here is quite similar. You can see the jagged line kind of does relate to it quite a bit. That's a 27-degree, if the surface of Guam is 27 degrees Celsius, that corresponds to 27 degrees Celsius without the greenhouse gases in place. And the reason we have a few of them is because a different temperature of the surface would radiate different levels of heat. So if Guam was a lower temperature, your jagged line would be at a lower radiant energy, lower amount of heat. So say as Lauren showed with the black body radiation, as you heat up a thing, it radiates higher and higher energy levels, as higher and higher it goes in the colours. Yeah.
Somebody once said that it's water vapor in the atmosphere that is indeed responsible for the greenhouse effect, and much less than carbon dioxide. So to what extent is that true?
Carbon dioxide is definitely the biggest. Does contribute quite a lot. It is also the highest of the sort of concentrates. But water vapor varies in its composition in the atmosphere. So sometimes it can contribute more. But I mean, carbon dioxide is a quite constant composition in the atmosphere, so 0.35, 0.37 now. Yeah. But water vapor, because it absorbs such a variety of wavelengths, you can see it absorbs all the way up there, all the way across. The little window that doesn't absorb in. So it does contribute greatly, but because it varies so much in the atmosphere, depending on humidity and stuff, depending on the heat of the atmosphere, the contribution varies as well. I think that's why carbon dioxide is often the most consistent greenhouse gas, I'd say. Okay.
Yes, I know you're
Sorry.
No, my question links to the point you mentioned in passing, Lauren. You mentioned, I don't know whether, I just want to confirm, did you say the sun is getting dimmer or lighter?
No, it's getting hotter and
It's
brighter.
getting hotter and brighter.
Yes,
So
in fact, with our primordial soup, it was a much dimmer, cooler world.
is that a
or
natural
dimmer.
process or what
Yes.
causes it? It's a natural process.
Well, we're certainly not impacted on the sun. Not yet, anyway.
It's the right thing.
Methane. I can't remember where I read it, but something about how's it pronounced? Methane flatrates. Someone know what I'm talking about?
Cultrates, I think. Is it the ice?
Yes. What's supposedly will go into the air if the ice
yeah.
melts. I mean, it's one of those slightly doom-mongering.
No. It is quite a hectic thing. I read the same article, I think, or at least in reference to. But methane is also another powerful trace gas. Like I said, carbon dioxide is the most abundant of the trace. But methane's in there.
But
And
methane's a lot stronger, a lot more potent.
Well,
It
it is, and
not coming out at the rates like carbon dioxide from industrial processes and stuff, but like you say, it's trapped in certain parts.
Yeah.
Like the permafrost, they must have a deep ocean, it's actually frozen on the seafloor. So what I think you were alluding to is that if it gets a lot hotter and it starts coming out and the ice melts, then that's going to kind of go towards a runaway effect, which is
Yeah.
something
that
which
happened
worries
on
quite a
Venus.
few people. But again, it's it's very difficult to study, so we're just going to have to hope that doesn't happen. But
Sure.
Now, I've once read that if Mars has the similar atmosphere to Earth, Mars would be habitable. So I mean, that's too.
well, Mars has frozen water. So if we could get it to a temperature equivalent to ours with a breathable, comfortable atmosphere, then the fact that it has liquid water means it has the capacity to have life. Liquid water, and I think we'll talk about it later in the course, is
What about just the temperature? I guess it had our atmosphere.
well, I think we should all bully Carl to his lecture on why water is the most essential ingredient for life, because it really is the most remarkable lecture, and we wouldn't have anything without it. So, and not just because it's good for his whiskey.
Since it's the point of the morning or whatever it is, how far does it have to go either side for this to become dangerous?
Well, it is 0.03. Well, in fact, I don't think I'm the right person to answer this.
If you don't know.
Well, I mean, I can hazard a guess, but I think you'd answer this a lot better than I would. So please do. No.
Or concentration.
How far does it have to go up?
Either side of
0.037%.
Either less or more for it to become a problem. I answer them. This is
But I mean, it's perfect the way it is now, and we know that by increasing it, we're already having a marked impact on everything from ocean acidification, which I will talk ad nauseum about if you buy me a drink, and on the other end of the spectrum, we obviously don't want our trace gases, our greenhouse gases to go too low because we want to have a warm planet. So yeah, we want to keep it as much to what it is now as it is, because this is where we've evolved to be. This is where we're our happiest. Okay.
Right, just as infrared rays will make it reflected, they get kept in our atmosphere.
Yeah.
I'm sure the same rays are getting reflected by particles, so light rays coming straight from the sun get reflected by particles in our atmosphere as well.
Absolutely.
That will have an effect on the temperature of our atmosphere as well.
That refers back to, I think, albedo, which Daniel was talking about. I mean, clouds reflect, particles in our atmosphere affect, ice on our planet affects. The way to think of albedo is, and the t-shirt example is really good, but I mean, you think of dark soils and dark forests, and they're actually really good absorbers of heat and of light. And the ice caps and our oceans actually reflect, I think, about 7%. And clouds, I mean, we can't begin to predict global warming. We don't even know what's going to happen with albedo. That's the greatest unknown. And I think George will talk more about that. But yes, of course it has an impact. Not everything reaches our Earth. And of course not all of the infrared that our Earth gives off as heat is kept in. A lot of it is lost to space. I don't know if that answers the question. Okay? Yes?
You mentioned that the sun is indeed getting brighter and brighter.
Right.
So probably this is when you think of Mars space, yeah, it's not habitable at the moment because the water is frozen. So do you think that there'll come a point where the sun will be so bright and emitting so much heat, the waters in the frozen water in Mars will melt and eventually lead to a habitable environment?
Well, you could say that. You could say we could move Mars a lot closer to the sun, and that would be Venus. And of course, Venus would be, was it minus 18? Minus 40 something. So even though Venus is closer to the sun, and a lot closer to the sun than Mars, even there, without its atmosphere, it would be frozen. So no, the answer is, even though the sun is changing, it's the atmosphere and its interaction with the light that makes it habitable or not habitable. And I think that's actually the key of the matter. I appreciate that question. Yes.
If the sun is getting brighter and hot, are we even fighting against the day or trying to create all the planet?
Well, look, I mean, I actually couldn't disagree
I
more.
say, like, I don't think the sun's not going to get bright enough in quite a long time, so it's not really our biggest concern.
Within your lifetime, you will start to see the changes brought about by global warming. Within your children's lifetimes, we can't even begin to predict what world they're going to be living in. The sun getting brighter is happening over hundreds of thousands of millions of years. And it getting brighter will probably be dealt with by our atmosphere, as it has continued to do for the last 4.6 billion years.
But is it worth?
Of course it is.
Trying to look at the issue of global warming.
Of course, because you are going to experience the consequences of global warming in your lifetime. Your children's children's children, in fact, you will probably have evolved into something entirely different if you survive global warming by the time the sun becomes an issue.
Yes, I understand, but coming from me, myself, coming from a social science point of view, I feel like this is just wasting of money, trying to take these millions and trying to
That would be,
improve
I would,
But what are you hoping to achieve by spending, in fact, not necessarily spending money, but
I'm trying to
capping-
create a habitable planet.
right, which we have, which we might not have within your lifetime. because of global warming. Not another 4.6 billion years where you might not be around anyway. You will have evolved into something entirely different. But now, right now, and your children's now, I don't know if you have children, I don't know if you're planning to have children, but within their lifetimes, they will not have the earth that we experience today if we don't do something about it now. Global warming is happening as we speak.
But can you stop the sun from becoming water?
No, so this was, it's not the fact that the sun's getting hotter, it's the our impact on conditions that have enabled us to live within a hot universe. I mean, the point isn't the fact the sun's getting hotter, that's what's creating global warming, but the impact that our actions are having here on our atmosphere to condition how that heat comes into it. And that's what we can have an impact on, just like we had an impact with CFCs.
Yes, that answered better. The sun getting hotter is not changing the atmosphere on the planet at all, because it's not changing the temperature on our planet, because the atmosphere is acting as an umbrella and a blanket to make sure that everything stays within range. So we have to protect the atmosphere, the thing that is keeping the sun constant. I didn't answer that very well.
I think we're setting the scene for this evening's event very, very nicely. Okay?
You want to know the rat?
Yes.
Thank you for answering that better than I did. Yeah.
A lot of those type of questions are stuff that we'll come around to towards the end once we've been through a lot of the science and social issues and then start to think about the kind of questions about what we should be doing comes a little bit after the kind of questions about what actually it is. We start by looking at why the planet is habitable and then look at what effect we're having and then we can start thinking about what we should be doing.
But Carl, I mean, the reason why the global climate change denialists or skeptics have such impact surely is the fact that they're able to challenge exactly this and what we're talking about, these basic.
Which is all the more reason to get straight
premises. Exactly. So yeah, I suppose that's why it's important questions like this come up now.
There are two questions that we're dealing with, and at the start we do the easy ones, and the scientists are admitted, which is the scientific question. They have a yes, no, or a numerical answer, which can be alluded to, and we can give error margins. The scientific questions are easy. Questions which start involving what we should do become social, political, they become far more complicated issues. They don't have yes, no, right, wrong answers.
But surely one of the most effective things that climate change denialist movements does is to say that the science that you're talking about with yes, no answers, that actually those aren't yes, no answers or cases.
And there again, because of our margin for error, we leave out so strong.
As soon as you say they answer it.
Or there is a possibility,
Yeah.
or we like to hypothesize that. Yes.
The yes, no answers in science are related because we do have skeptics. The value of skeptics of this is that they will force scientists to look more rigorously at the work that they are doing, and they'll help us then to answer those questions. But the scenario that we're in at the moment is that we've got basically a choice. You can become a skeptic and say, let's not do anything because I'm going to die. Or we can say that the prognosis that we have are likely to be correct, and therefore we should be doing something about climate change on the assumption that those prognoses are correct. The outcome of that is that within a number of decades we're likely to have a better world than we have now. It might not be exactly as we had predicted it would be, but it would be better. It could be a rising, or it could be much like this. And if we were to go already to simple rather fast analogy, we're in a situation now rather like a person going into a doctor. You probably come to me, I'm a fish doctor, I look at you and say, oh, I think you've got cancer, but let's leave it for a year or two. And then the symptoms will be really clear and you'll know what to do. Your decision is do I go and get a second opinion and actually treat the worst case scenario, which is that I have cancer, or do I leave it? And so essentially I think that we have to assume the worst case scenario, well possibly not the worst case scenario, but assume that things are going to change. And what we look at is what do we need to do to make sure that we are better off in several decades from now than we would otherwise be if we ignored it. And then the second point, the second question is certification, well, another aspect of the certification is atmospheric purification as well. So my question is, with the focus being so intense on the greenhouse gases, are we not tending to ignore the particulate matter in the atmosphere from the millions and millions of tons of biomass burning from this continent alone, increases the continental burning, and from industry, does give you dry from the atmosphere this time of the year? You can actually see the particulate matter.
Are you talking about the aerosols?
The aerosol, yes. Well, I'm not differentiating between greenhouse gases and they're basically the aerosol.
I mean, there are two such different scenarios. I mean, that took us like a week of lectures to sort of pull apart and unhash. But I mean, ocean acidification is not particulate matter in the atmosphere. Yeah.
No, I was saying, it's not ocean acidification, it's the equivalent in the atmosphere.
Absolutely.
Yeah, so nuclear
I don't know nearly enough to be able to answer any questions on this. I'm sure it will be dealt with. Yeah.
Call it a day. We're going to give you a nice early meeting, and there are a couple of announcements that I have to make. So thanks very much indeed. Okay, what we've really done today is we've just set the scene for tomorrow.